In this video, we are going to discuss how to calculate magnetic field at a point due to different segments of a loop. Let's start with question 8.85. The loop shown in the figure is carrying a current of 3.857 ampere and the distance r equals 1.411 meter. What is the magnitude of the magnetic field at a point P inside the loop? So here we have a loop that carries a current I of 3.857 ampere. The value of R is 1.411 meter, and we need to find what is the magnitude of magnetic field at point P because of the loop. Now the loop is divided into different segments. We can label them. Let this be segment 1, 2, 3, 4, 5 and 6. And we need to find magnetic field at point P because of all these 6 segments. Now the segments which are on the same line as point P, like segment 2 and 6, as well as segment 4. For these segments, magnetic field value will be 0. Because we know from Biot-Savart's law, magnetic field at a given point can be given as mu naught I over 4 pi integral I dl bar cross r cap over r squared, and this magnetic field will be 0 if I dl and r cap are along the same line, because when they are along the same line the cross product becomes equal to 0. So there will be no contribution to the magnetic field at point P because of segment 2, 4 and 6. So we are left to find the net magnetic field because of 1, 5 and 3. Now, since the same current flows through the loop, the direction of current through each segment will be the same. So if I take my current to be flowing clockwise, it will be clockwise in each segment, which means that direction of magnetic field at point P because of each segment will also be the same. And when I find the net magnetic field, which is the vector sum of magnetic field due to each segment, and since all of these magnetic field are in the same direction, we can just add them together. So B net will become equal to B1 plus B3 plus B5. 2, 4 and 6 we already established is 0. Now how do we find these magnetic field? We know that magnetic field at the center of a circular loop is given as B equals mu naught I over 2R, where I is the current through the loop and R is the radius of the loop. Now segment 1 is a semicircle. So when I find magnetic field at point P because of segment 1, I have to take half of this value. So B1 will become equal to half of mu naught I over 2 times R. Radius of segment 1 is 3 times small r, plus segment 3 is a quarter of a circle. So when I apply this rule for segment 3, I have to take quarter of this value. So we write this as 1 over 4 mu naught I over 2 times. Radius of segment 3 is 2 times r, plus segment 5 again is a quarter of a circle. So we take 1 over 4 mu naught I over 2 times. Radius is just r. Next, we bring the common terms together. We can take this mu naught I from each term and 2 times R from each of them as common outside. So we get B net to be equal to mu naught I over 2 times R. Now multiply the remaining terms and add them. Half times 3 will give you 1 over 6 plus 4 times 2 will give you 1 over 8 plus 1 over 4. And when you simplify this, you get mu naught I over 2R times 13 over 24. Now substitute the values to solve for this. Mu naught will be 4 pi times 10 to the power negative 7. I is 3.857 times 13 over 2 times R, which is 1.411 into 24. That gives you the net magnetic field to be equal to 9.298 times 10 to the power negative 7 Tesla. Next we discuss question 8.86. The loop shown in the figure is carrying a current of 3.961 ampere. The magnitude of magnetic field at point P inside the loop is 7.213 times 10 to the power negative 7 Tesla. What is the value of R? So here in this question, again, we have been given the current in the loop, which is 3.961 ampere. We have the net magnetic field at point P, which is P equals 7.213 times 10 to the power negative 7 Tesla. And we need to find what is the value of R. Again, as we discussed before, magnetic field at point P, because of any straight segment, will be zero. And there will be contribution to magnetic field only because of the curved segments. Straight segment, because they are on the same line as P, cross product of dl and r cap will be 0. So we only have to consider the curved segment here. So I will label the curved segment as 1, 2, and 3, and we can ignore the straight ones. So I get my net magnetic field to be equal to sum of B1 plus B2 plus B3. Again, we can just add all the magnetic field value to find the net because the current through each section of the loop is in the same direction, and hence the resulting magnetic field will also be in the same direction. Again, magnetic field because of circular loop at the center is mu naught I over 2R. Segment 1 is a semicircle, so magnetic field will be half of this value. So we write 1 over 2 mu naught I over 2 times the radius of segment 1 is 3R. Segment 2 is a quarter circle, so we get 1 over 4 quarter of this value. Mu naught I over 2 times radius of segment 2 is 2 times R. Segment 3 is also a quarter, so we take quarter of this value, 1 over 4 mu naught I over 2R. Again, take all the terms which are common together. I'm going to take mu naught I and the 2 R's outside the bracket. So we get B net to be equal to mu naught I over 2R. Now multiply and add the terms which are left. Half times 3 will give you 1 over 6 plus 1 over 4 times 2 will give you 1 over 8 plus 1 over 4. That gives you B net to be equal to mu naught I over 2R into 13 by 24. I want to find R, so we rearrange. I will move R to the other side and B net down. We get R to be equal to mu naught I over 2 times B net into 13 by 24. Mu naught is 4 pi times 10 to the power negative 7. I is 3.961 into 13 over 2 times the net magnetic field, which is 7.213 times 10 to the power negative 7 into 24. That gives you the value of R as 1.868 meter.